previous lecture, you notice that both the ends are put on a fixed point. Actually, this makes the system indeterminate because the number of external forces is now 4. We could make it determinate by putting the right hand side of the system on a wheel or on a roller. Let us take one example of this. And this is a very particular structure that I am taking. Let us take two rods, and I am making it very carefully, which are have a fixed joint here, one joint here, and I am loading it right here. This is just to again motivate and play around with forces and things like those in a truss. Now you see, if I start with this rod, let me call this 1, 2, 3, start with rod 1, 2, put it on a pin joint here and load it. The rod will tend to rotate like this. To stop that, what I do is I put another rod here, so that this is an isosceles triangle, and make a fixed joint on the other side also, and then the load is here. But the moment I do that, you see, if I look at this structure as 1, there is a load W, there will be reaction here, and in this case I know because the symmetry is going to be W by 2. Here also the reaction is going to be W by 2, and if I look at this pin here, from the support, fixed support outside, it is getting a force W by 2 like this, and is being pushed by this rod in this direction. So the net force on this will be in this direction. It will not be in equilibrium. To bring it to equilibrium, I add another rod here, and that makes a stable truss for me in this particular situation, where this is an isosceles triangle and I put the load on this joint. Let us analyze this further. So I have this structure here, and I have already argued that I need these 3 rods to bring it, make it a stable structure. If I look at this system, there is a force W by 2 acting here, and force W acting downwards. What I want to know is what is the forces in these different rods or members of the system. So let us call this 1, 2 and 3. Let us look at rod 1, 2. If I look at rod 1, 2, it is in equilibrium under the forces that are applied on it by this pin here and this pin here. Only 2 forces. And remember what I said in the beginning of the lecture, that if a body is in equilibrium under 2 forces, those forces are collinear. So in this case, there will be a force on this acting this way, and there will be a force acting on it this way at these 2 points. This is the only way these 2 forces can act. Otherwise, the body will not be in equilibrium. Similarly, on rod 2 and 3, there are 2 forces acting due to pin at 2 and pin at 3. Again, the forces have to be collinear. So the forces have to act in this manner, 2 and 3. And on the rod 1 and 3, again 1 and 3 is in equilibrium, the rod 1, 3 is in equilibrium. So the forces at 1 and 3 have to be collinear, because if a body is in equilibrium under 2 forces, they have to be collinear. So now we know the force directions. Let us analyze this further. If all the rods are equal, then all these angles will be 60 degrees. Now I know that pin 1 is in equilibrium. Pin 1 has a force acting on it which is W by 2. Since for the rod 1, 2, I made forces that are pushing the rod, so the rod would be applying a force the other way on the pin. Similarly, force on 1, 3 that I made was also pushing the rod, that is, the force is compressive. The force that will be acting on the pin would be in opposite direction. So, let me call this force 1, 3, this is force 1, 2, and this pin is in equilibrium under these forces. Since the forces are acting at one particular point, this I do not have to write the torque equation, only thing I will write is that summation f x would be equal to 0 and summation f y would also be equal to 0. This gives me that f 1, 2, this is 60 degrees, so would be this. So, f 1, 2 sine of 60 degrees is equal to W over 2, and that gives me f 1, 2. Similarly, summation f x is equal to 0. I recall that I am talking about this pin. On this pin, there is a force this way, f 1, 3, f 1, 2 and W by 2. This angle is 60 degrees. I am going to have f 1, 2 cosine of 60 degrees plus f 1, 3 is equal to 0, or f 1, 3 is equal to minus f 1, 2 cosine of 60 degrees, which is nothing but minus f 1, 2 over 2. F 1, 2 on the other hand, we found out is equal to W over 2 sine of 60 degrees, which is nothing but W over root 3, and therefore, f 1, 3 is equal to minus W over 2 root 3. I have found the forces on member 1, 3. I have found the force on member 1, 2. To find the force on the third member, that is F 2, 3, I have a choice. Either I can go to this point or this point and consider the equilibrium conditions there. If I go to point 2 here, then according to the way we have made forces, point 2 would be feeling a force this way, which is F 2, 3, a force this way which is F 1, 2, which we have already determined to be W over root 3, and a force this way which is W. Now, summation f x then gives you that F 2, 3 should be equal to F 1, 2. Of course, this comes with F 2, 3, this angle is 60, cosine of 60 degrees with a minus sign, plus F 1, 2 cosine of 60 degrees is equal to 0, and this gives you that F 2, 3 equals F 1, 2 equals W over root 3. So, we have determined all the forces in the system by looking at equilibrium of each point. One point I would like to make about F 1, 3 is that F 1, 3 came out to be negative. What that means is that the direction that we had assumed for F 1, 3, that is, we had assumed it to be like this, the compressive force is actually not so, it is a tensile force, that is the rod F13 is being pulled in this manner with force W over 2 root 3. For completeness, I should point out that the triangle that we just made should actually be fixed like this on a fixed pin on the left and on a roller or wheel on the right. This will make the system statically determinate. Through this, what I have done is provided you an example of solving for the forces in a truss through method of joints. That is, we take each joint, each pin at each joint to be in equilibrium. Now, a few subtle points about trusses. If I take these 3 rods and replace them by slightly wider members, with the width of the members being much smaller than their length, and instead of applying a pin joint, bolt them here by a plate. That is, each joint here looks something like this, and I put a plate here with bolts here. Even then, it is a good approximation to take this as a pin joint. So, a good to take a joint as a pin joint. Why? Because the width is very small, and therefore, even if there are little forces that are applied by these bolts, the torque produced would be almost 0, negligible compared to the torques that are applied by external forces, and therefore, it is a good approximation. By the way, the plate that is put here, and you notice it next time when you cross a bridge, is known as the gust plate. So, let us see now, given a basic truss like this which I just solved for, how can I make a bigger truss? Let us see, if I want to extend this further, I would apply, I put a member here and give a joint here. This joint now has 3 members that can provide equilibrium. Then this point, suppose I do not want to provide a support here, I have to provide one more member, and I could provide a fixed support here, a fixed support here. That is one possible truss. Another way is I have this basic truss which is fixed here, fixed here. I do not want to fix it here now. I provide one more member, so that this point now has 3 members that can provide equilibrium to it. This is a fixed point, and suppose I want to put this under a fixed point. Then this member has one force coming from the fixed support, one from this member. So, I have to provide one more member, so that there are 3 forces acting on it. But this gives a loose end here. I could fix this loose end by putting 2 members here. Now, you see each joint has a minimum of 3 members, so that this becomes a statically determinate structure. Let us see if it is. Number of joints in this case is 1, 2, 3, 4, 5. So, j equals 5 implies 2j minus 3 is 7, and 1, 2, 3, 4, 5, 6, 7 members, and therefore, m, which is 7, provides that this is a statically determinate structure. This is capable therefore of remaining in equilibrium when loaded. Several examples of trusses that you see in everyday life are, for example, Pratt truss, which you see Pratt truss, which is like this. It is put on the supports here and these are joints. Let us see the number of joints here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. So, 2j minus 3 is 21. Number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So, this is a statically determinate truss and capable of remaining in equilibrium. These points can be fixed. On the other side, either I can have a fixed pin or usually you put it on a wheel. I will comment on this a little later. Let us look at some other trusses in the meantime. The other one is Hoe truss, which is like the Pratt truss, except that the fixtures are the other way. Again, you can count the number of joints and number of members. They are consistent for it to be a statically determinate truss. Third one is a Warren truss, which is like this. So, these are different variations on the way the members and joints are fixed on a truss. And this side again I put it on a roller and this side is fixed. Again j equals 12 and m equals 21. So, they are consistent. J equals 12 and m equals 21. So, they are also consistent for them to be statically determinate trusses. Why we put a wheel here or a roller here is because what we have assumed in all this is that these members are rigid members. However, in reality they deform, and when they deform the distances may change, and to accommodate for that you put a roller here rather than putting it on a fixed pin joint, so that the stresses are not developed in these members. Notice that even when the wheel is put instead of a fixed joint, the truss is capable of remaining in equilibrium, since there was a redundant constraint on the system to start with. So, the question that we want to answer is, how do we calculate forces in the members of a truss, and that will be analyzing the trusses.